Hello and welcome to this episode for Electropages. I'm your host, Robin Mitchell. Today we're here at Avnet Silica and I'm joined by a very good friend, Thomas Hauer, from which we actually met in PCIM, and this is Avnet Silica. So thanks for letting us be here today.
Yes, you're welcome.
Fantastic. So today we're going to be talking a bit about EV charging. And we've seen so many different developments in the industry. We've seen things like wireless charging starting to sort of crop up in places. We've seen more charging points installed. We've seen challenges introduced with we're trying to get the power distributed. So I suppose my first question to you is, where are we currently at with EV charging?
So the last developments were DC chargers from 50 kilowatts up to 400 kilowatts. The main installations were like 150 to 400. That's where we are at the moment. But we're seeing some new developments on the higher range and the lower range.
Right.
The high range is megawatt charging, so it really does what it says. It's like charging up to a megawatt. That's meant for trucks. And the lower end we're seeing is like 11, 22, 40 kilowatts. That's the private and I would say semi-private office space areas.
Sorry, 11, that's quite low, 11 kilowatts. I'm surprised there are being developments made in that area compared to the fact that I thought people would want to sort of go towards the quick charging. So what's calling for the lower energies?
It's kind of a replacement for the AC charging wall box that you have, because for the 11 kilowatt, you can make it bidirectional, so you can charge the car and put it out again. And the 11 kilowatts is normally the usual household power.
And that's where you don't need that fast charging. It's okay. No. It's okay to charge it over a 24-hour period. Yes. It's just that, but you want a dedicated charger for that application.
Yes.
So let's talk about the 11 kilowatts, because this is quite interesting. So what advantage does that bring compared to your typical AC charger? You know, one you sort of just plug straight into the mains.
You have then access to the DC bus of the car, so the DC battery. Right. And it is then bidirectional, so you can charge and discharge. So for the moment, I think there's just one European OEM having a bidirectional onboard charger, and the functionality is limited. When you have the 11 kilowatt charger bidirectional, you have communication and you have your house automation, and this both can then talk to each other and increase the functionality of the whole thing.
So what you're saying is that the charger's moved outside of the car, and then and then the connection to the car is DC, which means that, okay, I'm with you. So by moving the charger away from the car, that's where you can put the advanced electronics inside the house. So you can essentially make it bigger. You can put more stuff in there, and then it means, like you say, you can have bidirectional charging, which you couldn't do with an onboard charger, because then it'd have to have an inverter as well.
The onboard charger, I mean, at the end, when you look at an onboard charger, it's a PFC and then a DC-DC, and you need to make these two bits bidirectional to make it actually work. And the complicated thing for automotive OEM is you need to comply to each and every grid provider standard globally. And this is a little bit of a problem. And for the OEMs, it's easier because they say, well, we have a DC connection. We don't care about what the grid provider wants. And that's then a local topic to be solved by the wall box provider, which they mostly already have done from a standards point of view.
And would it be fair to say, or would it be right to say that the majority of EVs tend to have the similar sort of battery voltages in terms of like the voltage they operate at, essentially?
Yes, there's this basically 400 volts battery, and then there's newish coming the 800 volts. So there's some models out there yet. One OEM has at the moment a big push in that direction. And I've seen already plans from OEMs that they even make smallish cars 800 volts.
And the increasing of that voltage results in a reduction of current, which makes it easier, or there's a higher power for the same current, which makes it easier to sort of put more power into both the battery and the wheels at the same time.
Yes, that's true. When we are DC charging at 400 volts, we're looking at a maximum power at 250 kilowatts-ish. Yep. And when we're at 800 volts, we're looking at 300 kilowatts, 320 for a longer time.
Yeah, which is a massive difference. Yeah. And so that also, even if it's for a shorter time, it still gives you that ability to sort of do the quick charging, where you can push a lot more power into it would that be the correct term? More power into it, more energy into it. You can push
more energy.
Push more energy into it in a shorter time, which then means that the time it takes to charge a car to get some distance is almost on par with filling up a tank of gas. But again, like you say, it's not just a case of the car's battery. It's every single component in that setup, from the energy distribution to the conversion to the connector to the car's battery. All of that has to work together to make sure that can happen. So in that conversation, how is Avnet Silica looking to sort of help that market in terms of and engineers solve those problems?
We're helping them on design decisions, where to go, which semiconductors to pick, which package they should pick, and then get, let's say, the most efficiency out of their product. Because the thing is, if you don't have efficiency, you need either a bigger heatsink or you need a fan. And do you want to have a big fan in your garage going off when you charge the car? No,
basically not. No.
And that's the big point. We need to make sure, as a supplier, to help the customer in a way that they can develop a product that's well received in the market.
So if somebody's designing, let's say, an 11 kilowatt charger system for a home or for a commercial space, and you sort of mentioned about how Avnet Silica itself will help to source those parts for engineers. What kind of vendors are we talking about that you guys have access to?
We have, when it comes to silicon carbide, we have 11, 12 suppliers that support with silicon carbide. There's ST, onsemi, then there is Navitas, then there's Renesas, then there is Nexperia, then we have Rome, Microchip, Wien, Punchit. Have I forgotten one? If so, I'm sorry. Yeah, so
We'll be back with you in a minute.
No, so we have plenty of suppliers, and each and every supplier has different strengths, and that makes it then for us kind of always a different decision, because some suppliers have these packages, some suppliers have other packages, and it always depends on the thing that the customer wants to build and the kind of mechanical geometry that's behind.
And I think that's where you guys differentiate compared to other sort of providers of hardware, which is that you guys you're not just going to source it and help distribute these parts. You're actually going to get almost get involved with the design itself in terms of the design consultation. So could you just sort of go through how that might work in a typical project? So let's say I'm a power engineer, I'm designing some charger, and I'm having some issues with sourcing parts, especially silicon carbide, because we all know that stuff is hard to work with, and it's not as trivial as a typical like NMOS transistor. So how does Avnet Silica go sort of beyond the sourcing?
So typically, if a customer asks, look, this is the specification I'm working towards too, and this is what I'm after, and we try to sit together with this person and work out, okay, what topologies this person has in mind. And then depending on the selection, we might recommend a different one or just stick with it. And then we try to find the right parts, or let's say the right silicon, to just start this whole thing. Mostly the customers start out with a, let's say, THT package, which is proof of concept, their idea, and later on they move then towards more complex packages like topside cooling or power modules and all that sorts of stuff. And we try to give them company over the whole process and be kind of a person of contact for them. It's like, look, I've seen this behavior. Have you seen this? Can you help? And can you advise? And then we just move forward. And also we help customers if they have a need for like a custom module, because we all know this industry standard ACEPAC modules, or ACEPAC is the ST name, FPAC, F1, F2 is for onsemi, for example. You can make them custom.
It really sounds like to me that Avnet Silica has got the engineers who are providing you the parts and then can recognize those parts, know what they are, and figure out where they've seen these issues before. Because I can tell you now that if I was to purchase parts from another company, like you say, let's say, for example, there's a particular silicon carbide chip, and some engineer before has seen it spike in a certain way in a certain application, let's say like a large back EMF or something like that, the chances are a distributor with sales reps is not going to be able to say to you, oh, by the way, watch out for this in your application, it's going to cause problems. They'll just say, here's your parts, thank you for your business. But you guys would step in and go, actually, might not be the best part for you.
Yeah, and that's actually what I just did recently in a customer visit, because the customer was very insisting on using silicon carbide in the future application. I asked them, okay, what's your setup? And they were like, inverter here, long cable in there, motor there. And I was like, nah, you're not going to have a proper product that works in a way you want it to.
I love that response. Nah, not happening. Love it. That's exactly what it should be. It shouldn't be a case of, oh yeah, that could work. No, not going to work.
Yeah.
Try something else, basically. And I think that's really great, because not only are engineers getting the expertise from you guys, but they're basically saving themselves money in the long run, because they're not going to start working on a chip, trying to sort of figure out why it's not working, only for you to tell them in hindsight, oh, you should have used a different one. No, you'll tell them from the beginning, don't use that part, use an alternative, or let us help you and get involved with the project so we can source the best parts for you.
Yeah, and what I'm always telling customers, look, we will not be able to save you from all of the questions that will pop up.
You can't invent it for them.
No, but what we're trying is to just get around the first questions, and then they get to the more advanced questions, and then we're back again to help them.
Well, essentially, you're trying to get rid of all the questions that have already been answered.
Yep.
We already know the answers too. So it's a bit like it's kind of like, oh, I'm going to use this part. Well, here are the top 10 things you've got to watch out for. Those top 10 issues shouldn't be cropping up in your design, because that's already been solved.
Yeah.
It's like you need to find out why your chip in your solution has a very unique issue that no one's ever seen before, and then try and solve that. So would you encourage, if let's say a customer does discover something like an unusual situation with a part, would you encourage them to send that feedback to you guys, so then you can then potentially bring that on to others who are also looking to do similar designs?
Basically, we love to have each and every feedback from customers, if it works, if it doesn't work. I recently had a customer visit where they were saying that, we are going to test the part, and I just directly asked him, please, can I have the test report, because I want to go through it detail by detail, because it's a custom part, and there always can be issues that need to be solved. And the thing is, it's not always possible for the engineer to share the data,
because that's like intellectual property.
And so if they can do, we're happy to receive the feedback. If they're not,
that's absolutely fine, because people have to keep some part of their. You can't release everything, and I appreciate that. But I think it is cool. It's certainly cool to hear that engineers might be who are out there might discover an unusual problem with the part or a sort of technology, and say, actually, tell other engineers, silicon carbide in this application can have really weird effects, and it may be something you want to avoid. And I think it's really cool. But we've gone a little bit off sidetracked here, because I want to go back to the conversation of EV chargers when you mentioned about the megawatt charging. Now, I'll be honest, I still can't get that. I still can't seem to conceive that, because a megawatt, we're talking power station levels of power.
Yes.
And I mean, not to be an EV skeptic, but I mean, if for example, if all vehicles were to switch over to EV, I mean, how would we cope with that kind of power load in the first place?
We're always talking peak numbers here.
Yeah.
And for example, if you go for a Tesla Model 3 or something, it says 255 kilowatts DC charging, but that's exactly from 10 to 25%. It's a quite short time, then it drops quite quickly.
Of course, yeah.
And so if you have a Tesla supercharger installment with like 30 stalls, one is arriving, the other one 10 minutes later, then 5 minutes, and then 15 minutes whatsoever. So the load is kind of constant. It's not kind of adding up and then staying there and then drops.
No, but it's still a significant load to add onto the grid, isn't it?
Yes and no. I did the math once for the central region. If we switch to electric,
central region for the UK, sorry.
No, central Europe.
Oh, central Europe. Yeah.
If we switch from today to tomorrow, all on electric, it's like 18% more electrical grid load.
But almost double. Is that 80%? 80% more, sorry, it's about double,
18.
Isn't it? 18?
1.8. Yes, it's quite low actually.
Oh, blimey, I thought it was going to double or so.
No.
Only 18%? Okay, so that's actually not that significant. So I suppose then if you're worried about energy distribution, I suppose more localized power could be a solution to try and ease the load as well across major grids.
And most of the people, if you follow the statistics through this whole kind of topic, most people drive to work and back, and this is on average a daily journey of 15 to 30 kilometers. So it's perfectly fine to charge the car either a little bit when you get back home or once a week. So it will distribute over time, and so
or just charge overnight when the demand goes down, so the lines aren't taking any more load than they would normally during the day anyway. So it's just a kind of sort of finding a way to sort of even that load out. And I suppose that comes back to that question about or the topic about the the ability to sort of both charge and pull power from a vehicle from an EV, whereby someone's got more power than they need, they can put it back onto the grid so somebody else can charge, and by doing that you can help balance the loads onto the grid on the grid itself.
And you also can use flexible tariffs.
Of course, so you can get paid to put it back on.
Yes, get paid to put back on, or also get paid to
charge during a low time. Exactly. But still, the megawatt chargers. What's the biggest challenge that a megawatt charger would face?
There are several challenges. I mean, megawatt charging is like 2.5 times 350 kilowatt chargers, and you need to have a 6 to 10 kV line going in there, then a transformer, and then it puts down. Because the thing is, when you go to megawatt charging, you always have to fit in 380 volts AC, three-phase.
Oh, absolutely. It has to be three-phase, yeah.
You cannot go higher with the input voltage because the silicon carbide semiconductors are not there yet.
So what's the maximum voltage that they can handle?
When you look at a Vienna bridge rectifier, you go with 380 AC three-phase in there, and the output is 800 volts-ish.
Right, yeah.
And the, let's say, standard voltage at the moment is 1,200 volts for the silicon carbide.
1,200, that sounds about right, yeah.
And there are developments at the moment going to 2.2 kV and 3.3 kV, but it's still not sufficient to switch on to the next grid level. Because when you talk grid levels, it's like the next level, I think, starts at 6 kV and goes to 10 kV.
That's So you got it's like you're a sub grid before it goes down to the 380s, and then you tap off 2 for each house. Yeah. It goes to 240. Yeah, that makes sense. So, and that's interesting. So that sounds like a barrier that the sort of EV charging, the silicon carbide needs to solve. Because if they could solve it, they would basically eliminate one whole step down.
They can, yes. They would eliminate, let's say, the kind of small transformers that they all need at the moment, but I don't see it coming in the next 10-ish years.
A long time, because it's such a huge difference. It's not from 240 to 380. That's not a very big gap, but from 380 is like 6 kilovolts to 11. It's just way too high.
I mean, there are inverter constructions for railways that can cope with that voltages. But they're not for EV charging. That's a different ballgame. No, we're talking thyristors and stuff, so that's a complete different.
Yeah, and I'm guessing field. They would have efficiency issues, or is it more of a?
Yes and no. Yeah, they're switching quite at a slow frequency. I mean, if
it's a thyristor, of course they're going to be in the hundreds of hertz, aren't they? Or something? They're not going to be in the kilohertz or megahertz. Yeah, that makes sense. Because the DC-DC converters, they tend to operate much higher frequencies, and that's where you can reduce the size of your magnetics, and that's where you can increase the you can reduce the. Hang on a minute. If you reduce the size of magnetics, you can reduce the weight, which also means you reduce the size of it, and then therefore you get a higher power density.
Yes.
Yeah. So therefore you can pack more power per sort of unit distance. Unit size, but in terms of the megawatt charging, even if you knock that down on your 380 volt line to 800 volts, so even if you've got a direct connection, how does that work in terms of safety? Because I mean, for someone like me, I understand that you can sort of design cables and connectors to be in a safe way, but what kind of safety concerns would there be in a situation where you've got a very high voltage charging system, where you've got a great big plug stuck into something?
For voltage, it's insulation that you need to apply. I mean, if you look at these megawatt charging cables,
they're huge. They're absolutely chunky.
And they're often also water cooled or oil cooled, so there's actually liquid flowing back and forth.
And to be specific, these are phones these would be for trucks. These are not these are not consumer vehicles. Yeah. These are like the big ones. Yeah.
Yeah, and they have a different plug than it's with CCS.
Oh yeah.
So you cannot mix it.
You can't plug. Of course, that'd be disastrous.
And so for the voltage, it's insulation. So you need to be sure that this is intact. So you can do insulation measurements before you actually switch on. So to just
so you can actually have active testing and sensing, so you can go, okay, this insulation is broken down, probably best not to use it.
Yeah, that's for example what PV inverters have to do every 24 hours when they're feeding in. They're making an insulation test every 24 hours. They just switch off, make a test, switch on again.
I didn't even realise that. That's good to know, actually, because it's one of the things that has always worried me a bit, is the idea of having really high voltage chargers, great big cables. Because I mean, like we all know what the outdoor environment can be like. There can be puddles, water everywhere. If it gets into the system, what issues is that going to cause? So that's actually quite interesting. But even then, a water cooled or an oil cooled cable, that's insane.
And it also feels quite weird when you first experience it.
Have you used one?
Yes.
What's it like?
It was a very warm and hot summer day, and I was just plugging it in, and for me it was a no-brainer. I was sitting in the car, I was like, where's the vibration coming from?
And it's the pump.
It's a pump. It's the pumps. It's not mechanically kind of insulated, so the vibration goes from the pump through the cable, and obviously the charge plug in the car is very like firmly mounted to the frame of the car, so very good for transporting vibrations. And so the whole car was starting vibrating a little bit. It's like, okay, geez, what's going on?
And that's a vehicle. That's not your truck. This is we're talking a consumer vehicle. So and so now when you talk about the cable getting warm, the first thing that I think of is that an efficiency issue. But then the size of the power that we're dealing with, it probably only takes a kilowatt or more just of wasted energy just for that thing to start to get warm.
If you use the thicker cable and the 450 amps for 250 kilowatt, it just gets hand warm, really. So it's like
it's not that much, really.
It's a temperature edge of, I don't know, 10, 15 degrees. So it's not that much.
I'm amazed that that it only gets that warm at 800 amps. Did you say? Sorry.
No, 450.
So 450 amps at
400 volts.
400 volts. That's goodness me. 400 volts at 4. See, this is the thing. And this is the thing I find absolutely amazing, is that if you look at any industrial environment where it deals with three-phase, you've got huge bus bars, big cables, people are wearing full masks when dealing with these cables, and then you've got a car charger which is dealing with far more power, and then you've got your average person just pulls it out of the car. Like the degree of safety is insane.
You always need to be aware of when you pull the plug out of either the charger or the car. There's no power, no.
I mean, it'll disconnect. It'll still just.
It's a physical insulation.
Yeah, but it's still the idea of that amount of power, like 10 centimeters in front of you. It's an incredible. I tell you what, it's an incredible achievement, to say the least, in terms of power delivery. And so I suppose, going back to the megawatt charging, again, what kind of challenges have you seen in that field compared to, let's say, the smaller ones? What would you say is the biggest issue?
The biggest issue, I think, is getting the whole system ready in a way that it's co-working efficiently, because you're not doing the megawatt in one charger construction. It's not kind of one dual active bridge or whatever. It's many kind of, I would say, blades or 19-inch racks, if you want to think in 19-inch racks.
Yeah.
It's many of these, and you need to kind of make them work together, and that's the thing. And that's, I think, is complicated, because when it comes to a megawatt, you have like many stages, and you need to get the cooling right for the many stages. You need to have the control systems right for the many stages, and that's a lot to think of. And on the long run, I do think we need to talk about arcing detection and stuff, because once this gets older and the plugs are a bit worn down and whatever, then you need to be able to detect arcing in the system and just stop.
And how would you detect an arc? Because that would just, because from a circuit point of view, that would just be a small consumption of current or a slight drop in voltage. How would you?
It's a drop in voltage, and you see it in the frequency response on the line.
Ah, does it oscillate, or is it?
No, it just increases noise.
Really?
You can detect this. This is what PV inverters, for example, have to implement now. So all the modern ones have this implemented to detect arcing in the PV installation on the roof.
So you're just looking at the noise level. You're not looking at the absolute voltage. If that makes sense.
No, because that could be misleading.
Exactly, because if someone plugs something in, it's taking needs a lot of current. The voltage will drop, which makes sense. But it's the noise floor that you're looking at.
Yeah, it's the noise. Normally, when you look at the input of to stay with PV inverters, is the input is always a boost converter, and the boost converter is quite friendly EMC wise on the input. So you measure on the input what noise is there, and you know, okay, from the start the noise is what my system makes, and if this changes in a way, you know, okay, that's something wrong. And the same is for the megawatt or kilowatt chargers. In the car itself, there's nothing really there that produces, say, EMC noise in a big scale when charging. So because there's just really the battery and some monitoring devices and disconnect devices, and the charger produces most of the noise. So if this one changes, then you can detect if there's anything wrong. So, and I think this is a long-term project, I would say, that we need to take on in the future.
Because, and that's because, you know, an arc in a megawatt charger would be, let's be honest, a completely disastrous situation because it's
very inconvenient,
huge amount of power, and that's really, but that's a really interesting problem to know about. So, if you'd asked me, I thought it would have been the load on the grid, but no, it's more likely to be the actual safety mechanisms behind the power delivery and making sure that system, when if it does fail, it doesn't cause any issues. Because we've all seen what happens when lithium batteries, for example, go up. They're absolutely horrendous. Unstoppable. So you don't want an unstoppable megawatt charger connected to an immovable lithium-ion battery, because that's going to be an absolute disaster.
Now, for the grid side of things, I think especially in Europe we're quite good sorted, I would think, because the grid providers in general do a really good job in providing that stuff. So it's, I would say that's my least worry there.
That's a really interesting perspective to listen to. I was really quite surprised by that, because now I'll be honest, I've never crunched the numbers, but I know what power distribution tends to be like, and I was always a bit worried. I was always a bit worried, thinking, do we even have the capability to sort of provide that power across if everyone switched over? But like you said, if it's only 18% extra, and you can encourage people to charge at night, provide them with incentives, which most people would probably do, that would actually alleviate that issue. And that's a really, really interesting point of view. Never thought about it like that. But in terms of, so going back, so again, one more question about the megawatt chargers actually. Because in terms of the solutions that Avnet Silica is looking to provide for engineers, and let's say look at the technologies actually. What technologies do you think are going to be key to these kind of chargers, do you think? Because you also mentioned about the fact that you have them in racks, so obviously you can parallel these sort of systems up. So you can, you know, reduce the voltage, reduce the current, that down. So you can use a smaller device for each one. So what kind of technologies do you expect to see integrated into those applications?
It's widely a silicon carbide application. We need to see and wait a little if GaN evolves towards that kind of voltage, because GaN is at the moment quite limited to 650 volts, and if you have the DC link voltage at 800, I mean, there's no point to use it there. So that's something we need to wait on. I mean, there's lots of smart people working on kind of the future of GaN at the moment. There's lots of movement in the market, and but for the moment, it's mainly silicon carbide. For the gate drivers, I do see mostly capacitive insulated gate drivers. They have some advantages in delay times and jitter and stuff, so it's also more easy to make, and it's then kind of more, I'd say, more easier process. So it has a tinier price tag, to be fair.
And I think that's an interesting point to mention, which is that silicon carbide, which we will talk about in a later video, is the technology that everyone's sort of looking towards for high power, but it also has its own issues. Like, for example, the need for gate drivers compared to like traditional silicon devices, which are quite easy to drive and they're very well known. In how to do that, the silicon carbide devices, if I remember correctly, are a little bit more complex, because you can't just pulse a voltage signal on them and expect them to work. You do need to carefully ramp those signals and check the transients.
Yes, you need to switch fast, and you always need to look at the device itself, because most of them have gate resistors built in, so it's not like plug and play, just to use one and then just glue the other one in and you're fine. Also for silicon carbide, compared to silicon, is you need to have a negative voltage to switch off. I mean, you can theoretically stop at 0 volts, but you need to be aware that...
You need a hard stop, so you need to go even lower, and that helps to just sort of close that channel completely.
Yes, because the thing is, if you're switching off at 0 volts, there is gate charge left.
Exactly, and it's going to go, ooh, and then you get that resistive part, and then all that current is going to be going through, it's going to heat the device up.
In theory, it is switched off, but the risk is if you have a surge over the drain, you have accidental switch-ons and stuff. And the active Miller clamp, yes, it will help you, but just be safe and switch off.
Be safe and come down lower, but that's why you need that gate driver, because you need something to generate that negative voltage if you're working on a single power supply to bring it down. And to bring it down appropriately and carefully timed as well.
That's the point. You need to have proper timing, you need to have proper switching, and you need to have proper parameters. I mean, they're the logic, let's say logic level silicon transistors that you can theoretically drive out of a microcontroller. It's not that easy. Not
going to happen with this. Okay, so that's an interesting point. Do you think there's going to be a situation in the future where sort of some microcontrollers might have specific silicon carbide gate controller outputs? Or it already exists.
For IGBTs, they do exist actually. It's the STM32 ST Spin 32 cool. From ST. It's a Cortex M4F, I think. They do have gate drivers for motor control incorporated, but it's mostly IGBT gate driving levels. So it's a job you actually can do, yes. What you need to be aware of if you integrate this in a package, so if you have, like, say, the CPU die and then the gate drivers dies, you produce losses in there with switches and stuff. And you need to be aware that this might be an issue for packaging and cooling the part.
Oh, right, so the gate drivers themselves could get warm, as in like during operation?
The current generation of gate drivers can drive up to 6 amps, and there's plans to go up to 10 amps.
Oh, so really? Yeah. 6 amps to gate drive?
Gate drive, yes. But we're talking peak, but still.
But still, still. But still, that's a huge peak.
Yes. And for IGBTs, we were long talking about like half an amp or 1 amp or something.
Yeah, but that's still a lot less compared to the 6 amps you might get from a peak on a... I didn't realize that silicon carbide had such a high inrush current to charge that gate. If
you switch fast, no matter what the capacitor looks like.
Oh, it's going to... Q. Oh, is it? What's the equation? Oh, is it? I can't remember the equation now, but Q is IT. So it's DI... No, help me here. What's the equation for change of charge over time? Is it...
You have the capacitor integrates the current over time.
Yeah.
So what you're doing is actually...
differentiating it.
You differentiate the current.
Yeah, so it's di dt, isn't it? Yeah, that's the one. Yeah, that's why even if it's a tiny capacitor, the fast rate of charge, I think, results in a very high. Yeah, the smaller dt, the larger it must be on the di. So that's why you get that sudden going right up. Okay, and that comes down from the faster switching, which is advantageous because you have smaller magnetics, but the cost is that you might have issues with things like EMF. You can have issues with things like inrush current, gate driving, like you mentioned. That's really interesting. So. Does that mean, would you say that means the nature of EV charging and sort of like, just sort of power handling in general, the nature of the problems is now shifting away from what it used to be into a new realm?
The old problems are still there. The problems got more. That's
more problems, not
more
less.
Problems, yes.
It didn't change, it just got more problems. That's brilliant, fantastic. So just before we wrap up this video, I've got one more question for you. For those watching this video at the moment and they want to get involved with Avnet Silica solutions for their next EV charging application, what would you recommend that they do?
Call us or write us an email. Go on our website, we have a contact form, just write us, find us on LinkedIn.
Find him on LinkedIn.
Yes, find me on LinkedIn.
Add him, message him. That's perfect.
And then just write us, get in contact with us.
Fantastic. Brilliant. Thank you ever so much for taking the time to see us today. Thank you very much.